Welcome back. We are now ready for part 3, which is going to be shadows. And as promised, you're going to see that there's a sort of continuum from vanishing points and vanishing lines to reflections to shadows, somewhat surprisingly in terms of the underlying geometry. So we're, of course, extremely familiar with cast shadows. Go out on a sunny day on any given day where the sun is obviously the dominant light source, and you will see your shadow being cast onto a surface. And it turns out, I mean, when you look at a picture like this, you think, wow, the geometry of this has got to be really complicated. The nature between the relationship between a cast shadow and its object, particularly like here with the shadows being cast onto multiple surfaces. Well, it turns out when you look carefully, this geometry is in fact quite simple, and it is again dictated by straight lines. All right, so let's do the following. Imagine, if you will, for me, a three-dimensional world. So I realize I'm showing you an image, but I want you to try to think about this in 3D. I have a flat planar surface, I have an upside-down ice cream cone, and I have a single tiny little point light source right there illuminating the scene. Yep. So imagine this out in the three-dimensional world. And of course, what you're seeing is some fairly obvious things. The floor or the plane onto which the cone is resting is a little bit brighter underneath the light. That's illuminating downwards. This side of the cone is brighter, and this side is darker, like the dark side of the moon. And we have a cast shadow on the ground to the left. Now, again, in the three-dimensional world, imagine I take a point right at the tip of that cast shadow and pull a string until it connects to the tip of the cone. Those are corresponding points, of course. And I just keep going. Well, what's going to happen? I'm going to hit the light source. Why? Well, that's the definition of a cast shadow. So let's go in ever so slightly from that cast shadow and play the same game. Draw a string. What's going to happen? I hit the cone. Why? Well, because that point is in shadow. It's not being illuminated by the light. Now, go just to the other side of the shadow, pull the string. What's going to happen? I hit the light source, or I hit the light source because the light is visible to that point. So right at the tip to tip, shadow to object, I will intersect the light source. Okay, good. So that's a pretty simple geometry out in the world. For every point on a cast shadow, I've drawn a line to the corresponding point on the object, and it will intersect the three-dimensional location of the light source. By the way, in this case, I've drawn the light in the image plane so you can see it, but obviously take that light and yank it out as far as you want to infinity and beyond, you will still have that line. Now, in the last slide, I said, well, shadows look pretty complicated, multiple surfaces. What happens when we move away from, for example, a planar surface onto which the shadow is being cast? Turns out, nothing changes. So, let's look at this slide right here. I've got this dome, the cast shadow where the tip is now hitting that curved surface. And look what I've done. I've connected a point on the shadow to a corresponding point on the object, and I've pulled that string outwards, and it intersects the lights. This geometry that I just described to you is completely independent of the underlying scene geometry in the three-dimensional world. Yeah? Same thing. Take that, go back to that bike shadow, we could do exactly the same analysis. Okay, so that was in the three-dimensional world. We draw a string from a point on the shadow, corresponding point on the object, draw it out, we hit the light source. Let's take an image of the scene now, what we've been seeing all along. Well, what happens under linear perspective projection, i.e. no lens distortion, to straight lines in the world? They image to straight lines in the image. How do I know this? Well, first of all, we've been doing that since we talked about vanishing points and reflections. Straight lines in the world image to straight lines. Now, parallel lines in the world converge to a vanishing point, but they're still straight lines, just the orientation is different. Same thing here, same thing with reflection, same thing with vanishing points, same thing with vanishing lines. So under linear perspective projection, that is, there's no lens distortion, then in the image, I now have a correspondence between three things. The projection of the point on the shadow, the projection of the corresponding point on the object, that's obvious. And what is that? Well, that's just where the light would project to in the image. Now, in this case, it's sort of trivial. I can literally see the light projects just like any other point in the scene. If that light was outside the scene, well, I would have just had to carry it out and there'd be some virtual projection somewhere outside of the frame of reference. So now we have a linear constraint on points on the cast shadow, corresponding points on an object, and the light source that is illuminating the scene. Now, obviously, in this example, there's only one light source. That's what makes the analysis easier. There's only one shadow. If I had another light source here, I'd have another cast shadow there, and I'd have to do two analysis. So for now, let's consider the case where we're outdoors. There's a single dominant light source, the sun, relatively simple and straightforward, and that's the cases we'll work on now. Okay, now, you can see why this would be a really powerful forensic technique, because now I can walk around an image analyzing if all the shadows are consistent with a single dominant light source, for example, the sun. Of course, unfortunately, the world is not speckled with these very detailed little points. That cone is always very nice. The world is often filled with these sort of amorphous looking blobs, a lot like my head, by the way, an amorphous blob. There's no really distinct point on my shadow. There's just sort of this sort of circular looking thing, and there's this circular looking thing on the ground. And so if I pick a point on that cast shadow there, what do we know? We do know that there is a corresponding point on the object such that when I draw a line, I will intersect that light source. That geometry hasn't changed. That's exactly the same. But now I'm going to ask you, well, what is that corresponding point? Well, here, of course, you know, because you can see the light, so you can just draw the line and figure it out. But if the light's not in the scene, there's no way of knowing. There's nothing distinct about that shadow, and there's nothing distinct about the object. And it seems like we're sort of stuck. So we could say, all right, fine. Shadow analysis only works for highly distinct features, but that's not very rewarding. I think we can probably do a little bit better than that. So let me propose the following. So let's take that point on the shadow, and let me make the following argument. I may not know where that line is right here that you see that connects a point on the object to the point on the shadow to the light source. That's obviously the right answer. But here's what I do know. I do know that the point that is occluding this surface from the light must be somewhere between that top red and that bottom red line inside of that wedge. So that wedge, of course, that I show you there goes to infinity all the way out, right? And here's what I know. I know that the light must be somewhere in this region, okay? So obviously not as tight of a constraint as somewhere on the line, but notice also when it's on the line, there's an infinite number of places it can be on the line. It can be really far away, somewhere closer, very close. So there was always an ambiguity. There's just like a bigger ambiguity now. Now, maybe I'm being a little conservative here. Maybe I could have tightened up that wedge because I know that that point's probably not on the bottom or the very top, but let's be careful. Let's just be conservative and say it's somewhere along there. So is that helpful? Well, sure. Is it as helpful as having the linear constraint? No, but we have more than one shadow typically in a scene. We have multiple objects and multiple shadows, and we're going to start to see how we can put these together to start to reason about the light in the scene. Now, you may have noticed that the cast shadow that we've been talking about, where one object obscures a different object or surface from the light source, is really only one of the shadows in this scene. What's the other one? It's right on the object itself, and that is called an attached shadow. So notice here that that part of the potato-like object is facing the light, it's illuminated, and the part that is not facing it is, well, it's not illuminating. That's the dark side of the moon. By the way, you may be wondering why, if the backside of that object is not being illuminated by the light, why isn't it black? You know, I can still see it. And by the way, since we're talking about it, why isn't the cast shadow black? That's because in this rendering, I have an ambient light term. That is, we model light with a directional light, that's what you're seeing casting the shadow, and then this overall ambient light of the light bouncing around the room and then uniformly illuminating, obviously not causing a shadow. And that's why the dark side of the moon, the back side of that object is not black, and that's why the cast shadow is not black. Okay, so let's get back to the attached shadow. So you can see that at a point right there where it goes from illumination to darkness is an attached shadow. What you do is you take that point and you draw a line that is perpendicular to the gradient from, parallel to the gradient from bright to dark, and that is called the terminator. It's called the attached shadow terminator. And what we know, and I won't derive this for you, but I think it's fairly intuitive, is that the projection of the light source that gave rise to that attached shadow must be in the half plane determined by the terminator. Okay? And I've just drawn the little dotted line there so you can see where the right answer is, of course. And that's sort of intuitive. If this side of my face is being illuminated, well then the light must be somewhere over here. And whether it's up or down, I can't really tell because I'm just being illuminated. But as soon as the light flips over to here, this side of my face is illuminated and I've got a half-plane constraint. By the way, notice this is just a generalization of the cast shadow. The cast shadow is what? It was a little wedge-shaped constraint. Well, just open that up to a half-plane and you've got a different constraint. So this is sort of the same constraint, it's just how big it is. And again, I mean, it doesn't give me a huge amount of information, but can we agree it gives me some information? I know that the light isn't any over here, but it's got to be somewhere on this side. And so the game we're now going to play is we're going to start to cobble together these attached and cast shadow constraints to try to reason about whether the light in the scene is consistent with a single dominant light source. Again, let's stick to outdoors because obviously indoor lighting is a little bit more complicated. So in this case, for example, I have a cast shadow here with a wedge constraint. I have an attached shadow here with my attached shadow constraint. The intersection of those, and you can see already that I've started to narrow in a little bit. I know, for example, that the light cannot be, not very much information, but it can't be between the shadow and the object. It has to be somewhere out in this polygonal shape here. And then obviously as I start to bring in more constraint, I start to slice and dice and constrain that space. And eventually, hopefully, we get down to something relatively small and we can look for consistencies or inconsistencies in the lighting. All right, so let's talk about how you formulate these now. You could do this, by the way, in a drawing program. It's not that hard, but it's always nice to formulate these things the same way we did with the vanishing points and the vanishing lines. So let's start with the attached shadow constraint. It's a little bit easier. All right, let me introduce some notation, please. Vector x is the 2D location of the projection of the light source in the image. In all of our examples, these have been in the image plane, but of course they can be anywhere in the infinite plane, horizontal or vertical, just some point in R2 in the plane. Okay, that's what we're trying to figure out to constrain the position of, right? We're trying to figure out if the shadows in the scene are consistent or not. Let's again, starting with an attached shadow, take a point on the attached shadow where you drew the terminator, and let's call that the vector P. So x is a 2 vector, point in R2, P is a 2 vector, point in R2, and let me define that vector n as the unit length vector that is perpendicular to the terminator, okay, and rooted, of course, at P. Okay, what do I know? I know that the x must lie to the right of this space. Well, how do I formulate that now that I have a little bit of notation? The way we formulate is pretty easy. We're going to say that the dot product, so again, remember that x, n, and p are all 2 vectors. So the dot product of n and x, surface normal and light position, minus the dot product of n and p must be greater than or equal to 0, and that tells me that x must live in this half plane. By the way, why is that? Let's get some intuition for this. All right, let's look at the first term. What is n dot x? It is the dot product between the surface normal and the projection of the light source. Forget about the NP for a second. I'll come back to that. So what does it mean if the dot, so what is the dot product, by the way? Let me remind you, row vector, column vector, scalar value. It is proportional to the cosine of the angle between the 2 vectors. And what I'm saying is that value must be greater than or equal to 0, which means that the angle between them must be between minus 90 and 90. That's all I'm saying. That NP term is just because that vector n isn't at the origin. And so when I subtract NP, I'm just sticking that thing at the origin. And now I can compute the dot product between the direction of my plane, direction of my light source. If that is, the cosine of the angle is between minus 90 and 90, I'm in the half plane. So that little equation here says for a given P with terminator, with surface normal n, I can constrain the projection of the light source that it must satisfy this inequality. Again, n is known, p is known, x is unknown, and we're gonna start stacking up these constraints and ask, is there an x that satisfies all of the constraints? Good. So that's the attached shadow. That's pretty straightforward. Cast shadow seems a little more complicated because we have this wedge-shaped thing, but let's look at it. I've got a point on the shadow that's p, and I have 2 linear constraints. I've got the upper one, where that little n1 vector is perpendicular to that upper line, top of the object. I've got the lower line, where n2 is perpendicular to that lower line, the bottom of the object. And my x, of course, is still the projection of the light source, which I'm trying to figure out if it's consistent with all of these constraints. Well, if I have one, so what do I want? I want that wedge-shaped that is consistent with both of those lines. Well, what is that? Well, let's just do N1. It says that it's in this entire half plane. What's N2? It's this entire half plane. If I intersect those, can I agree that I get that little wedge shape, which is what I want? So all I have to do for a cast shadow is write two constraints. N1 dotted with X minus N1 dotted with P is greater than or equal to 0, and N2 dotted with X minus N2 dotted with P must be greater than or equal to 0. That's just two linear constraints. Okay, so all cast and attached shadows can be specified as linear constraints. And once you have these linear equalities, you just throw it into a linear program. These are off-the-shelf, MATLAB, Python. You just give all the constraints, you specify P, you specify the normal, you pack them into a linear program, and let them figure out for you whether there is a consistent value or not that satisfies all of those linear constraints. Okay, now, turns out there's a little rub here. I've been slightly lying to you. Okay, so let me fix that lie because it's important. All right, let's look at this panel right here. This is what we've been talking about all along. It's a top view of the geometry of the scene we've been thinking about. I have a camera down here. The back of the camera is over here. The aperture or the lens or the pinhole of the camera is there. That looks a lot like a camera obscura that we saw in the background section. And out in the world, again, bird's eye view, I have an object that's shown in gray. I have a light source that's shown in yellow. And I have a shadow that's shown in black. And what did I say? I said take a point on the shadow, connect it to the point on the object, and extend it outwards, and you will hit the light. And I said that is true in the 3D geometry in the 3D scene. That's correct. That's what I'm showing you right here. Now, image those 3 points. Here they are. Now, in the image, I have a point on the shadow, point on the object, and the projection of the light source. Same linear constraint and the same order. Shadow, object, light. Good. So everything works out. I've not lied to you here. Here, something is a little bit different. Okay, I've got my object, that's the gray point. I have my shadow, that's the black point, and I have my light over here. Now in the 3D world, everything works. So let's see. I take a point on the shadow, draw it to the corresponding point on the object, and extend it outward, and I get the light. That's absolutely correct. But notice now that the light, unlike the object in the shadow, is behind the camera, where this is in front of the camera. Now you may be saying, well, if the light is behind the camera, I can't see it, it can't project into the image. No, it still does. It's a virtual projection. Just do the geometry. Take that point on the light, draw a line through the aperture, and where it strikes from the back, the sensor, is the projection of the light source. So notice what happened here is that the object in shadow image down below, and the light images back here, but here's the rub. Look at the connection now between object, shadow, light. I'm going from the object to the shadow to the light. Why? Because the projection of the object and shadow didn't invert, but the projection of the light source did. This is the negative sign on the perspective projection. Since this has a negative z value, it cancels the negative value on the perspective projection. This does not, and so you get an inversion. And so there's in fact 2 constraints you have to worry about in the image. 1 constraint in the world, shadow, object, light. 2 different possibilities in the image, shadow, object, light, or object, shadow, light. And so when we do our analysis, we always have to do 2 analyses depending on whether the light is in front of or behind the camera. Obviously, I don't have to worry if the object or the shadow is behind it because I won't be able to see it. And if I can't see it, I can't draw the constraints anyway. All right, just a little bit of a sort of technical glitch you have to worry about here. So the game we're going to play is we're going to have a scene. We're going to manually identify all the cast shadows and the attached shadows. And let me emphasize that this is a manual analysis. Computer vision is not able to find reliably shadows in the image. And even if it was, it certainly can't tell you what object cast it. So this requires a human analyst to build these constraints in the image. Specify all the cast shadows, specify all the attached shadows of your user interface, but then you have to consider in your linear program the forward constraints and the inverse constraints. And the inverse constraints are easy, you just negate everything. And all of those details are in a series of papers that I will point you to so you can see exactly what the equations are for that. Now, if neither of these are satisfied, well, then we have a problem. All right, let's now apply this analysis to this video. All right, terrific. So that's the slow motion that you're seeing there. Eagle swoops in, grabs the baby. Father realizes he's not paying attention. Uh-oh, I'm in deep trouble. Baby drops to the ground. Everybody's fine. Okay, so this video went viral, oh man, a couple years back, and eventually showed up at my desk because it had made it into the mainstream media. And this is sort of the action shot. Yep. You got the eagle, you got the baby, you got the negligent father, you got the carriage, you got this sort of structure in the background. And by the way, notice this person all the way over here, which I mentioned because you can see a shadow. Okay. Now let's agree on a few things. This is outdoors. There is a single dominant light source, which is the sun. And since we don't care about the geometry of the surface onto which all these shadows are being cast onto, we should be able to run our cast shadow analysis and see if all of these shadows are in fact consistent with a single light source. Okay, I'm not going to do the forward and the reverse. I'm going to go ahead and just tell you that the forward analysis doesn't work, that the light is in fact behind the photographer. And you can sort of see that I'm standing here and notice the direction that the shadows are going in, which would suggest that the light is behind me. Don't guess, by the way. Do the forward and the reverse. Check to see if one is consistent or not. And you'll know right away, because when it's not consistent, the constraints go in all kinds of crazy directions. All right, so what I've done is, since it's in the reverse, I'm going to go from object to shadow to light, not shadow to object to light. So I took a point on the father's head. I drew a cone or a wedge shape. And of course, that has to extend to infinity. Yep. Now, I'm going to do the same thing for the carriage, for the structure in the background, and for our friend back here. Now, remember I said that unlike the linear constraints, these wedge-shaped constraints aren't quite as precise. But look at what happened from 4 constraints. Look at what happened. I went 1, 2, 3, 4, and look at that little wedge-shaped area right here, right? That little trapezoid. That now is the projection of the light source in the scene must live in that little trapezoid right there. So just from 4 constraints, look at how much I've been able to constrain the projection of the light source. By the way, we got a little lucky. This person is our friend. The best type of analysis is when things are spread out across the scene and the constraints come down very hard on each other and carve out the space of R2 to give you this very nice tight constraint here. All right, so that seems to be perfectly plausible and consistent. Now let's look at the baby and let's look at the eagle. All right, let's start with the eagle. I've got a point on the tip of the wing and I've drawn it down. And it might be hard to see here, but it does in fact intersect that little trapezoid. Just barely it nicks the corner. So the eagle is actually consistent with everything in the background. But look at the baby shadow. The baby shadow goes off way to the right, nowhere even close to where it belongs, right? And obviously the shadow and the baby are consistent, which is right there, but they are not both consistent. And this says that, and this is off by quite a bit, by the way, that this scene is not consistent with a single dominant light source, and something is wrong. And in fact, if you have not seen this before, you now know that this is a CGI composite. The eagle and the baby were computer generated and superimposed atop live action. So everything you saw was real. The father, the scene is everything real, but the eagle and the baby are completely computer generated, illuminated with their own light source. They did a pretty good job, by the way. If you looked at that original scene of those shadows and you didn't draw these constraints, I don't think you would have noticed this. It's pretty subtle. And so they got it sort of right, as running in the right direction, but not quite right. Okay, and you can now show that unambiguously this image is a fake. Let me just show you another analysis. This is one of my favorite analysis. This was, so the work I'm describing is that of Eric Key, who was a graduate student in my lab many years ago. And as we were doing this analysis, we were just going on Flickr looking for images to analyze, and this was one of our favorite ones. Showed this total hippie dude over here with these like hardcore cyclists over here on the Washington Plaza, and we thought, there's no way this is real. I mean, this just seems like a really unlikely image. In fact, when we did the lighting analysis, again, the light is behind the photographer. You can see that because the shadows are running away from me. A little hard to see all the blue constraints in the dark background. I apologize, but that little white outline there is the intersection of all the attached and cast shadows that that we annotated there. By the way, we contacted the photographer of this to ask him what the story was behind the photograph, and it turns out that the hippie and one of the cyclists were old high school friends and happened to run into each other on the plaza. They'd obviously gone a little bit different ways in their life, and it was like their little reunion, and that's where the photograph actually came from. Turns out it's a real photograph. Now, obviously, if the shadows and the lighting are consistent, it doesn't really prove that it's real, but it starts to at least move away from, clear evidence of manipulation. When you get, especially with lots of different shadows cast and attached, when things are consistent, that is often very difficult to get right when you're manipulating an image in a 2D photo editing software. But again, it doesn't prove it. You guys all know how this works. A lack of evidence isn't evidence of anything. It's just a lack of evidence. Okay. By the way, in case you were concerned, we just went ahead and analyzed the moon landing image. I don't think it's going to shock anybody here that the shadows here are perfectly consistent. People have, by the way, been arguing for decades that the lighting and the shadow in this image are wrong. They're completely bonkers. We analyzed, I'm just showing you a subset of these attached shadows, which are shown in dotted lines. The cast shadows are shown in solid lines. I'm just showing you a subset of them. They're all perfectly consistent with a single light source. And here I really do know that there's only one light source out there, which is the sun. So I'm not so worried about the moon landing conspiracy. Okay, those are cast shadows. And again, notice that it's linear constraints, right? That's it. We just drew lines. Well, we drew wedges, but those wedges are made up of two lines. So the attached shadow is a single line. The cast shadow is two lines. Those give you inequalities. You package all those up. You shove them into a linear program. And what you now need is a little user interface for specifying those shadows. Relatively easy and straightforward to do that. We have a couple of different user interfaces that we use. We built one in JavaScript, which actually works very nice in the browser. We built one in MATLAB. Unfortunately, not one in Python. Okay, so we now have vanishing points, vanishing lines, reflections, and shadows, all of them relying on this very simple geometry of lines, linear constraints. And again, you see this beautiful connection between seemingly disconnected things of shadows, reflections, and vanishing geometry, that they share this really interesting and, more importantly, predictable geometry. And what's important here is that we are leveraging expected geometric properties of the three-dimensional world, going through the linear perspective projection process, and what do we expect to see in the image, and then making those measurements. And again, I've already talked about this, but I'm going to emphasize it again, and we'll talk about this later on in the class, is that pure visual inspection of these things is very, very difficult to do. And so these types of analysis are really good to have in your toolkit of forensic analysis. All right, I'm going to stop there. We'll pick it up in a little bit. See you soon.